Hi everyone! Let's continue programming shaders whose code fits on a single line. This time we'll create an effect called dithering, which in this case means rendering an image using a heavily limited color palette. So let's get started. You can probably guess that we won't be able to squeeze any amazingly complex algorithm into a single line. Well, in theory we could, if that line were several hundred characters long, but that would greatly reduce its readability. The point of this mini-series is to demonstrate simple algorithms that we can later build upon to create more complex effects. So, just like the last time, I'll create a new scene with the usual image in the background, that is, a screenshot from our game Whispers of Prague. Let's do all the preparatory work. So I'm right-clicking the scenes folder, create new scene, and let's call it simple dithering. Okay, is it correct? Yes. And dragging the mentioned image into it. So the sprite 2D node was automatically created, and in the inspector I'll do the usual stuff: expanding offset and cancelling centered, expanding transform and resetting position to 0, 0. Okay, and let's not forget to scroll down to the materials section and create a new shader material. Click it and add a new shader, which is called simple dithering.gd shader. Type shader mode canvas item, and I'll put it as usual to the folder shaders. Create and clicking again to open it in the shader editor. And as always, I'll delete everything from the generated code that we won't need for our effect, leaving only the fragment function. Deleting vertex, deleting light, and saving. Okay, and we can start writing code. As I said at the beginning of the video, it will be a single line inside the fragment function. So I'll write its basic version first, and then we'll keep improving it. Okay, and the line would be this one. Color equals the function texture applied on our texture with the standard UV coordinates. Okay, so we don't see any change, of course, because this code does exactly what a completely empty shader would do. It reads the pixel value at the current coordinates and renders it at the same coordinates to the output variable color. But our goal is dithering, so instead of the actual RGB color values, we need their approximations. For that, the step function will help us. As we know from previous tutorials, a step function returns 0 on 1, depending on whether the tested value is below or above a given threshold. So let's try applying the step function with a threshold of 0.5. Let's add it here, step of 0.5, and this pixel value. Okay, and here's our first result. It's obviously nothing groundbreaking, and it's not the expecting dithering yet. But even so, we've managed to render the original image with a reduced palette of just 8 colors. How is that possible? Let's take a look at what the step function actually does. As we know, the texture function returns a color in RGBA format, so it's a vector 4. However, the first argument of the step function is a float, a number. So in this case, it's a shorthand for applying the function to each component of the vector. It is therefore equivalent to the following code. I will just paste it here. So it's basically the same. Let's comment out the first line, and we can see the result is the same. So we have a vector 4, which consists of 4 steps, each applied on the particular component. Very well, so let's revert. It was just for demonstration. And for creating an RGB color, we are interested in the first three components. And since they are a result of the step function, they can only take values of 0 or 1 in this case. That gives us exactly 8 possible combinations, which we can see in this table. Okay, so no other RGB values can be obtained in this way. Of course, we can change the value 0.5 to achieve a different looking effect. So if I change it to, for instance, 0.2, it is definitely very different, or maybe 0.8, it should be very dark. Yeah, let's get back to 0.5. Okay, so we could also replace the constant 0.5 with some variable, for example, the x-coordinate of the current pixel. So let's change it to uv.x, and I'll open more of that. Okay, however, the dithering is about simulating more colors than are actually available in the palette, using various combinations of colored dots. That means that for further improvement of the algorithm, we'll need a more complex function. Let's see what happens if we apply a sine function to uvx. Sine of uvx. Wait. Okay, so almost nothing happened. Obviously, the x-coordinate alone isn't enough. So let's add the y-coordinate plus uvy. Okay, so we achieved some darkening on the right side and at other sides as well. But otherwise, it's not much of an improvement. But wait, we are getting close to something more interesting. Now we'll introduce a simple pseudo-random element into our shader, which this dithering is based on. The principle is elementary. We multiply the sine function by some large number, for example 1000, and then take the fractional part of the result so that we keep the output in the 0 to 1 range. So instead of sine, we'll use fractional part of this sine. Okay, very well. And now, as I said, multiplying by 1000. And now we have some kind of a pattern. So far, we've increased the amplitude of the sine function. This is this number. Now let's improve it, improve the frequency in the same way. So inside this sine function, let's multiply uvy by 1000. Okay, that's better, but I don't really like these horizontal artifacts. So let's increase the amplitude to 10,000, adding one more 0. Okay, we'll make one more adjustment because this kind of dithering works better in linear color space. So let's apply gamma correction. It would be like this. So instead of texture UV, I'll use power function and to the power of 2.2. And since we are using a vector, we need to use the vector as the second argument as well. So vector 4, 2.2. Is that correct? One more bracket. Very well. We've achieved the effect I showed at the beginning of the video. If we wanted to fine-tune it further, it would certainly be useful to turn the numerical constants into uniform parameters. So let's do it. And I'll put them to the start of the script as usual. Uniform float x for simplicity with a hint range, and it starts at 10,000, our current value, and let's make it from 1 to 10,000. That's too much, and the step can be 1 in this case. Okay, now let's do the same for the y, but this time it would be only 1,000. So y, and finally the gamma correction. So uniform float gamma in range, and as we know 2.2 is usually the best value, and let's make the range from 0 to 10 with the step point 0.1. All right, and we can now replace what? Yeah, this 10,000 by y, this 10,000 by x, and 2.2 by gamma. Okay, and let's find parameters in the inspector and try some experiments. So if I decrease x, we can see how it gets some stripes with low values, or for y, yeah, something else. But I still think that these initial values, 10,000 and 1,000, are the best. And of course, gamma, make it brighter, make it darker. Also, it can be an interesting fade in, fade out effect if we want to. Okay, one last thing. If we wanted to add a bit of motion to the final effect, we could introduce a time variable, which we'll control using a parameter that I usually call speed. So let's add this parameter. Uniform float speed with a hint range, and let's set the default value to 5, and the range would be from, for instance, 1 to 10 again, and the step point 0, 1. And we'll insert its usage into our line, and specifically right here. Is this correct? Yeah, I think so. Plus time times speed. Okay, I hope it is observable on YouTube as well. So now we have a very interesting motion, which resembles something like a distortion of an old TV. If I change speed, it should be faster or very slow. And of course, setting the parameter to 0 stops the motion completely. Okay, and we are completely done. And it's still true that even in this final effect, we used exactly 8 colors. Thank you very much for watching. This dithering is of course not perfect and exhibits certain visual artifacts which become especially noticeable when zooming in. But perhaps that's precisely why it's suitable for cases where we want to simulate a similar kind of imperfection, just like in the previous video where we were creating frequency modulated chaos. In the next video, I'll return to this topic once more and show how to program dithering in a more classical form using a Bayer matrix. But until then, take care, good luck with your projects, and I'll see you again next week.